The Home Office Fire Experimental Unit, based at Moreton-in-Marsh, has been investigating the advantages and disadvantages of the sprays that can be produced by high-pressure and low-pressure pumps on fire appliances. This involved extensive fire tests in order to make a realistic comparison of their performances. In support of this work, a fire test room at their hangar at Little Rissington was developed to withstand test fires modelling the fiercest domestic single-room fires likely to be encountered. The room is 4.3 metres square and 2.7 metres high, with an open doorway and two large windows. These windows provide considerable ventilation, but they can be blocked up when the effect of poor ventilation is being studied. The fire load was placed in 3 cribs, one 3.4 metres long across the back and two 2.7 metres long at each side. These contained a total of about half a ton of wood, all of which had to be kept within closely defined moisture limits. The fire generated about 6 megawatts of heat, the equivalent of 6,000 one-bar electric fires. 44 thermocouples were placed near the top tiers of wood to monitor the progress of the fire, together with separate thermocouples which measure the air temperature at ceiling height and at waist height in the doorway. In this room, it is possible to conduct controlled fire tests safely in a way that can be reproduced again and again, so that comparisons can be made between different tactics and equipment for extinguishing fires. In these tests, the trials officer started the fire from his seat in the control cabin using detonators in trays of flammable solvent placed under the cribs. The solvent burned for approximately 2 minutes and set the wood alight. In what became the standard procedure, the fires were left to develop for 8 minutes until they had reached a steady temperature. The thermocouple's temperature readings were all displayed in front of the officer in charge of the trials as a series of thermometers showing the progress of the fires. The information was also recorded for subsequent analysis. Video recordings were made using specially cooled cameras placed low down in the doorway, as well as ordinary video cameras looking in through the windows. A thermal imaging camera was also available if the obscuration was too severe. The trials officer selected the most appropriate view of the fire and could watch the computer display of the fire's progress. For most tests, the hosereel branch under test was mounted on a turntable so that it could be swept backwards and forwards at a controlled rate without placing the operator in danger, and so that the variable effects of the branchman's skill and the versatility of the branch could be excluded. The water supply in all the tests was kept constant at a flow rate of 100 litres per minute using flow meters. When the water was applied, a large amount of steam was generated, and this frequently obscured the fire. But the thermocouples continued to tell the trials officer how well the firefighting was going. After the water had been applied from the doorway for a total of 2 minutes, the turntable was pushed further into the centre of the room, and the water was applied from there for the remainder of the test. In this series of fire trials, 8 different hosereel sprays were used to fight the standard test fire. To obtain valid comparisons between the effects of the different sprays, it was necessary to set all of the hosereel guns to give the same spray cone angle and total flow rate. These remained constant throughout each trial and were the same for all trials. The values chosen were 26 degrees included cone angle, which would completely wet the front face of all cribs, and a flow rate at 100 litres per minute, since this flow rate could be provided by most guns. The gun pressure required to give this flow rate varied between 4 and 35 bars for the various guns used. Within each spray of this general shape, it was necessary to know something about the mass distribution of water in a cross-section of the spray, and also the droplet sizes and droplet velocities present. The various sprays could then be categorized according to these characteristics. Mass distribution trials were undertaken using a sampling rig capable of collecting 18 samples simultaneously. The rig was systematically traversed across each spray, collecting samples for a set time at a number of fixed positions. The samples captured were accurately weighed, and the resulting data used to construct contour plots to show where the water actually went within each spray. These plots showed wide variations in water distribution from spray to spray. A longitudinal plot was also made for each spray to help assess throw. Droplet diameter measurements were undertaken for the FEU by a company in the USA using high-speed photography techniques and video and computer processing to provide both droplet size and velocity data. The results showed that all of the sprays contained a very wide spectrum of droplet sizes, but the mean drop diameter only varied by a factor of 2 from the finest to the coarsest spray. Generally, though, it was found that the higher pressure sprays did produce finer droplets. Armed with all this information, the next step was the fire trials themselves. First, the coarsest spray, that is, the one with the largest mean droplet diameter, was used to combat the standard test fire. This was followed by the finest spray. Next, a third spray was used, which had a mean droplet size similar to the fine spray, but an average droplet velocity similar to the coarse spray. Each of these trials was carried out 3 times to confirm that the results would be the same on different occasions. The results confirmed this, and also showed that there were some differences in fire suppression performance between the 3 sprays. They could now be arranged in order according to how well each had suppressed the trial fire and cooled the air in the doorway. This result was checked both by manned trials and by halving the room ventilation. The results from these further tests confirmed the previous ranking order and demonstrated that the standard trial was a fair one. After this, a single fire trial was performed using each of the remaining 5 sprays, for which spray characteristics had been measured and an overall ranking order established. A typical fire temperature record of an average fire looks like this. The fire temperature builds up for the first few minutes and then stabilizes at a temperature of about 800 degrees centigrade. The progress in firefighting can then be split up into 3 phases. When water is first applied from the doorway, the air temperature drops rapidly as the hot air in the room is displaced by steam. The second phase covers the progressive extinction of the fire as it's brought under control. After 2 minutes, the branch is moved further into the room and the fire temperature again drops. After a short time, it's apparent that no further progress is being made, although it's clear that the fire is under control. Normally, a firefighter would then continue to extinction, the final phase, by a close-range attack on the remaining hotspots. Clearly, a simple sweeping rig cannot do this, but the success of this phase depends far more on the abilities of the firefighter than on the spray patterns and droplet sizes of his branch. The trial results were compared with the measured spray characteristics to discover which characteristics or combination of characteristics were most important in achieving good fire suppression. During phase 1, the finer sprays, generally, cooled the air at the doorway faster than the coarser ones, because finer droplets are more readily turned to steam in the hot environment of the room. This also happens if the spray can be directed at the fire, but in a real situation, the firefighter may not know where this is. The steam that is generated drives the hot gases out of the room by every available exit. This rush of steam and hot air will endanger the firefighter in the doorway. During phase 2, the only broad trends which could be detected were, firstly, that generally the lower velocity sprays were preferable in suppressing the fire, and secondly, that the sprays should be in the form of a solid and uniform cone. In this phase, high pressure offers increased throw and possibly increased flow rate. Once the water was being applied directly to the fire, variations in droplet size seemed to have no significant effect. Normally, a firefighter would then continue to extinction, the final phase, by a close-range attack on the remaining hotspots. But the success of this phase depends far more on the abilities of the firefighter than on the spray patterns and droplet sizes of his branch. For practical firefighting purposes, the tactics employed should be governed principally by whether the firefighter can see the seat of the fire.
I can't say anything, John. I'll just go...
The main conclusions drawn from the work can be summarized thus. Branch versatility is important because of unpredictable conditions, and the spray should be a solid and uniform cone. Tactics are very important. The way in which any good hose reel gun is used has more effect than any subtle differences in spray characteristics. High pressure capability gives the firefighter more options than low pressure alone. Any extra pressure available could be used to give an increased flow rate at a given gun setting, or give a longer throw, or give a slightly finer spray, which is useful when rapid cooling of the air is the prime objective. The work is fully documented in an FRDG report and will later be published as a CFBAC research report for circulation to all Chief Fire Officers. This program of trials has served to underline the fact that high-pressure pumps are valuable to the fire service, not because of their ability to produce finer droplets, but because they increase the available water flow and range.